Hello everyone, this is Bahubali Farande. Now we will discuss on beam strength of bevel gear and how we can find out the beam strength value for the bevel gears with a reference of beam strength value of spur gear, because when we can consider the size of the cross section of the tooth of the bevel gear varies along with the face width. That's why directly we have find out the value of beam strength for the bevel gear is impossible. That's why we have considered a formative spur gear, a virtual number of teeth for that consideration to determine the beam strength of the tooth of bevel gear. To initially we can consider elemental section of the tooth at the distance x from the apex O. See in figure, you will see here we can consider one elemental section, because that bevel gear cone section varies. This is the smaller end, this is the larger end, and it varies. That's why we have find out the actual force acting at the midpoint of that face width. That's why we have initially assumed that one elemental section, that's a dx element, the size of that element is a dx and distance from the apex point is a x. Here we can consider, and by using Levy's equation of formative spur gear, the elemental section, we have considered the equation here, delta SB, that delta, because we have considered beam strength of the elemental section, that's why delta SB, because original formula is SB is equals to MB sigma BY, but here for the elemental section, the formative spur gear, beam strength value is a delta SB, here we can assume is equals to MX BX into sigma B into Y. MX is a module of the section for that particular considering section, and Bx also face width for the elemental section. Bx is also equals to dx, that size of that element, and sigma B is a stress, and y is a Levy's form factor for that elemental section, depends upon virtual number of teeth. This is the formative spur gear equation for the dx element. Okay, then we will discuss here. We have considered here one of the ratio. First of all, you can consider here one triangle. Assume initially the triangle O. Here we can assume the A point and one of the triangle, and here C point. This is the one triangle because of the Rx and R, and for the ratio of the A1, A0 and X. For that purpose, before going to that ratio, first of all, note down those points or remember those points. B is a face width, dx is a element size, and B is a total face width of that bevel gear. A is a cone distance, and X is a distance from the apex of that element. Y is a pitch angle. Rx is a from the central neutral axis distance of that element, and Rx is a larger end distance from the neutral axis, and A0 is a larger end distance from the apex point. X distance is a distance from the apex point to the dx element. Dx element distance from the apex is a x, and SB is a beam strength acting on at the midpoint of that gear, face width of that gear, and this is the direction. That's why here we can take one of the ratio is here. Which ratio? For that purpose, Rx divided by R is equals to x upon A. That ratio comes from here. We can considering one element. What is the ratio? Rx divided by R divided by x divided by A0. Take the ratio here, x divided by A0. How it comes? Because here we can consider one triangle. I am tracing here this triangle. From that one imaginary triangle here, this is and the size is Rx, and when we can change the larger end point to again one triangle here. Consider here these two triangles are same angle, pitch angle. Then these are the equal triangles, making adjacent sides are ratio of that adjacent sides are also equal. That's why we have taking that two triangles. This is the first triangle. From that midpoint we can again make one perpendicular on neutral axis. Then this this triangle, and again we can larger end, again it's one of the triangle. These two triangles we have considered two imaginary triangles. Then these are the two sides, and these are the same two different sides. That's why same triangle making ratio of the adjacent side of that two triangles are also same. That's why we have taken the ratio Rx divided by R is equals to x upon A naught. That's why here we can taken that ratio Rx divided by R is equals to X divided by A naught. That's why here we can say from the figure, and Rx is equals to XR divided by A naught. We can rearrange the formula. Rx is equal to, take the R denominator to numerator and XR divided by A naught. Okay, at the elemental section, we have considered the module for that element section. Mx is a module for that elemental section. General formula of the module is equals to d divided by z, but d, that's a pitch circle diameter indicated by 2 times Rx, because Rx indicating the elemental radius. That's why here 2 times R divided by Rx divided by z, and z is the number of teeth. Then what is the value of Rx? Put up that Rx value here, XR divided by A naught. Then Mx value, module value is equals to 2 times x, small x divided by small x into R, capital R, divided by z into A naught. This is the module formula. Then at the larger end, this is the elemental section module, and when we can consider larger end of the two, here this is the larger end. At that time, what is the module? Module is equals to again pitch circle diameter divided by z, but diameter we can consider here 2 times R divided by z, which number of teeth. Then from the equation C and D, compare these two equations. Here mx is equals to m, put up the value here, then we can find out the value of x divided by A naught. R get cancel, and finally we can got the module mx for the normal module for the elemental section. Mx is equals to m is a normal larger end module into x upon A naught, and already we have discussed bx is equals to dx, because this is the size of that elemental section and this is the face width for that elemental section. From that equation E, F, this is the bx value, mx value, and from the previous equation, this is the A equation. Here we said this is the first equation. From that three equations, we have put up the value of delta SB is equals to m sigma b y x dx divided by, put up the equation, and from the equation number B, that B equation and G equation, put up the value of Rx here. We can put up that value here, and then sigma b is equals to mb sigma b yx dx divided by A naught. This is the value for delta SB, and again we can take the one of the for the elemental section here. For the elemental section, we have taking one torque moment, or we can consider torque of that element. Torque is equals to force into perpendicular distance. Here force is equals to delta SB. Here is a SB, total beam strength, but when we can consider that total dx element, at that time the force element delta SB here and SB into perpendicular distance is a Rx, because here we can take the moment and we can find out the torque. Torque is equals to force into perpendicular distance. Force here delta SB and perpendicular distance is equals to Rx. That's why here we can consider delta SB into Rx is a torque moment. That's why here we can consider that's a empty value, and again for the same stage we have taking the integration with limitation, with considering lower limit to upper limit. A naught b, here consider here A naught b, A naught minus b to A naught. This is the lower limit and this is the upper limit, with taking integration on both sides. That integration gives the value of mt, and here m sigma b y r divided by A naught, these are the constant terms, and taking the integration x square into dx, and x is a variable term, because elemental section, in that elemental section we have considered x distance. Sometimes we have considered this element, sometimes we consider this element, but this x is a variable term. That's why here we can take the integration for that x, and all other parameters are constant. That's why with considering lower and upper limit, integration x square dx is equals to x cube divided by 3, and lower limit to the upper limit, then put up that value lower limit and upper limit, then you can got that equation 1 minus b upon A naught plus b square divided by 3 A naught square. This equation with respect to mt, mt is equals to total equation comes from that equation, mt is equals to, then finally we can got that equation. But beam strength for the this is the elemental section torque. When we can consider the torque for larger end, at that time torque is equals to, here for that larger end, torque is equals to, here we can consider the one of the force also. Here we can elemental section. Now we can take an elemental section, but now suppose we have taken that larger end. At that time, the torque is equals to beam strength divided by here torque is equals to force into perpendicular distance, and force is a beam strength, that's a SB, and perpendicular distance is a R. That's why here we can taken the value MT is equals to torque for the larger end, torque is equals to SB into R, and compare these two equations. MT is equals to this something and MT is equals to SB into R. That's why here we can taken that values. SBR is equals to this total term, but here we can rearrange that formula. SB R get cancel, this R and this R get cancel, and then finally we can write down that equation. SB is equals to MB sigma by in bracket 1 minus B upon A naught plus B square divided by 3 times A naught square. But here in last term, actually for the face width of the bevel gear is limit to 1/3 of the cone distance. Okay, larger end side is already safer side, because the P effective load beam strength value of the larger end always greater than P effective load. That's why 1/3 section we have cone distance we have considered. This is the 1/3 cone distance, and we have considered that value. That's why the last term we have neglected here, because for the bevel gear we have considered only 1/3 value of 1/3 size or 1/3 cone distance from the apex point. That's why this distance we have avoided, because larger side P effect beam strength value of the larger end side is always greater than P effective load. That's why design is same. That's why we have considered only 1/3 section of the distance from that cone, from the apex point or in that cone. That's why here we can neglect that value and take finally that modified equation. SB is equals to MB sigma by into 1 minus B upon A naught, and here SB is a beam strength of 2. This is the module, face width, sigma B, and Y is a Levy's form factor, and A naught is a cone distance, and finally that particular term is called as bevel factor. That term is a 1 minus B upon A. It gives the bevel factor. This is the beam strength equation for bevel gear. Okay, and from that equation we have considered we have find out the value of larger end side is when we can comparing the larger side value tangential component. At that time the value is always greater than P effective load. That's why we have considered the mean value. That's why we have considered, sometimes we have compare that value RM value. If that part already covered in force analysis part, that's in VB Bhandari also 19.3 point section number 19.3. that part already we have discussed, and you can check that value, the RM value, and you can consider the value for pitch circle radius, the larger end side, and finally you can use that equation, and that finally assumption or final conclusion for that gear, beam strength should be always more than effective force between the meshing teeth at the larger end of the tooth. This is the truth for all bevel gears. Okay, this is the beam strength. And lastly we have considered the face width of the bevel gear is a 10 times M. 10 times M means it's a module, otherwise A naught divided by 3, which is a smaller, not a larger, which is a smaller. Take that face width value for the design consideration. When in numerical they are not given to the value of face width, at that time you can assume the 10 times 10, that's the general value, but only bevel gear 10 times M module, 10 times module, or A naught divided by 3. In that two equation, in that two options, which value of face width is a smaller, you can take that value for the further calculation. If any query related to derivation, ask me. Thank you very much.